Hello, everyone. Thanks for the nice introduction. My name is Lukas.
My name is Lukas too.
And welcome to our talk about TLP-based location disclosure attack. So our talk initially starts with a timing side channel on the TLP, the translation look aside buffer. Then we show that exploiting allocator and defense behavior allows us to amplify the side channel leakage from the TLP side channel. Then we show that using this side channel leakage, we can perform reliable and stable kernel exploitation. And lastly, we show a live demo showing both the side channel leakage as well as kernel exploitation. Again, my name is Lukas Ma. I'm a PhD candidate at Graz University of Technology. I specialize in system security, kernel security, side channel security.
My name is Lukas Giener. I'm a postdoc at Graz. I'm doing secure caches, secure cache architectures, and microarchitectural attacks.
OK, before starting with our work, let's talk a little bit about the motivation of kernel exploitation. In kernel exploitation, threat actors typically start with initial code execution in an untrusted and unprivileged context. The goal of these threat actors is to exploit vulnerabilities to perform privilege escalation to root. They do it by initially exploiting a vulnerability within the kernel software, which allows them some kind of override capability on some kernel metadata. This, on the other hand, enables them a read primitive which returns one or multiple kernel addresses. Then, in the second stage, these threat actors exploit either the same or a different vulnerability to, again, get some kind of override capability of other kernel metadata. This enables them some kind of write primitive, which corrupts kernel data with attacker-controlled values. Then, in the next step, these threat actors typically trigger kernel events, which internally use these corrupted data from the previous step for either a control flow hijacking attack or for data-oriented attack to finally performs the wanted privilege escalation.
So this looks like it already works pretty well. So what's the problem here?
Actually, there are multiple problems. So when you exploit a vulnerability in software, especially in the Linux kernel, you put the system in an unstable state, which potentially leads to exploitation failure. Another potential failure is converting the capability of a vulnerability in something like, of a read primitive requires exploitation techniques which are also inherent prone to failure. This is true for read primitives as well as for write primitives.
So how bad is this for our attacker?
So what might happen is it leads to either an immediate system crash or potential immediate system crash, or it potentially crashes the system later on.
So the attacker just waits for a reboot, or?
Unfortunately, no, because a system crash usually leaves some kind of unwanted artifacts in the kernel, let's say in kernel logs, which then potentially triggers forensic investigations. From threat actors' perspective, this is bad because now these system crashes can undermine the stealth of kernel exploit. And these system crashes potentially, therefore, burns valuable zero-day vulnerabilities from the threat actor perspective.
So we can, of course, do better, right?
Yes. Let's go back to the former example of we have the capability of overwriting some kernel metadata. And let's imagine we have a magic wand. This magic wand now allows us to convert these limited and, in a lot of cases, solid capabilities to an arbitrary read-write primitive. An arbitrary read-write primitive is, in a Linux kernel, basically God mode. Then what you can do, you use the arbitrary read-write primitive to perform the privilege escalation attack.
So that's a very nice magic wand, but where do we get it?
That's a very nice magic wand, that's true. We will show it in the work, but before we define two challenges which our work solves. The first is we have this override capability and we need to know where to write. And the second challenge is we need to know what to write. And with the overall goal, it should be as reliable and stable as possible. To do so, we define this roadmap with both challenges on the left, so challenge 1, where to write, with a goal of finding the location of target kernel objects with 3 intermediate stages, and on the bottom for the second challenge, what to write with 1 intermediate step, the wanted God mode arbitrary read-write primitive.
So for the first part, I think I have some idea how we can resolve some of those question marks. So I've heard of disclosure attacks with TLB timing side channels. Do you think that could be of use?
Yeah, but what's a TLB?
Okay, that's a good question. So let's go one step back even further. How do virtual addresses get translated into physical addresses? So for this, we first split the virtual address into 9-bit segments, and then we use these 9 bits each as an index into tables. So these 5 tables then successively get closer to the final translation from the virtual address to the physical address. So now we've translated it, and we know where in physical memory our virtual address is.
But isn't it really slow, because now we have 4, 5, 6 memory accesses only for 1 translation?
Yes, so CPU vendors thought the same thing. So this is where we get to the TLB, the translation look-aside buffer. This is a cache that stores recently used translations from virtual addresses to physical addresses. And on Intel CPUs, it might look something like this, where we take a virtual address, we take out, let's call it here set index 1 and 2, we XOR them, and we use this 8 bits as an index into 256 sets in the TLB. So this is how large the TLB is, 256 sets, and each set has 6 ways, or in other words, 6 possible translations that it can store in this set. And so to find if our virtual address is stored in one of these 6 ways, we just compare the tag, that is the address, and if it is in there, then we get a translation back. We get the physical address. And this then only takes 1 to, I don't know, a few cycles. So it's much, much faster.
So, but now we have a timing difference in whether this translation is cached or not cached?
Right, so there is a timing difference. So let's see how we can find out what that is. So this is actually pretty simple. We start some cycle-accurate timer. Then we do an access, a simple access, which necessitates this TLB involvement. And then we take the difference to a timestamp afterwards. And that will give us how long this access took.
But when we attack the kernel, and we are not allowed to access kernel addresses.
That's true. So this would, of course, fail if we did this for a kernel address. But there's a nice little trick. We can use the prefetch instruction. So the prefetch instruction is a hint to the CPU that says, please load this address into the cache for me. I'm going to use it probably very soon. And crucially, this doesn't actually architecturally access this address. And so our program doesn't get a fault if this is actually a kernel address. But this still does the TLB access, this translation. And so we still see the timing difference here. And when we do this over many addresses, we can create a histogram that looks something like this, where we can clearly see that pages that are unmapped, that is, pages that can't be in a TLB at all, can be clearly distinguished from pages that are mapped. And within pages that are mapped, we can easily tell the difference between hits, that is, pages that have recently been accessed and therefore loaded into the TLB, and pages that have not been accessed, so they're not in a TLB.
OK, but now if we have accessed a kernel page, it is loaded into the TLB. How can we remove this cache translation?
Right, so I think what you're getting at is if I want to remeasure an address that I have accessed, then I need to get it out again. So let's go through an example here. The kernel does some kind of access, and this is our TLB set, and this gets loaded into the TLB. And so now if the attacker comes along and does their prefetch, it's going to be fast. And if the attacker now measures a different address, they're going to have a slow prefetch. But this slow prefetch still loads it into the TLB, and if we were then to do this again, it would be fast the second time. So we can't get any new information like this. And so this attack is called the evict and reload attack because we do a second step. We evict by filling the entire TLB set with other addresses that we have. And because we know this function, this XOR function, we can tailor our addresses to fill exactly one set. And now we're at the starting state again, where we can do another round of measurements on the kernel. All right, and so now that we have this, we can try to leak the region basis for the kernel memory. So the kernel organizes its memory something like this, where it has regions for the direct physical map, vmalloc, vmemmap, code, and modules. And all of these have randomized offsets between them. And so for exploitation, it would be nice if we know where all of these start. And we can find this start by using our mapped or unmapped distinguishing primitive. And then within these maps, these regions, if the kernel doesn't access, we can use our accessed or not accessed primitive to find this location. And this location, of course, has page granularity because the TLV stores page translations. And so for most of the kernel, this is going to be 2 megabyte pages. Does this solve our challenge?
Yeah, does this solve our challenge? Now we have this intermediate step where we can leak 2 megabyte aligned kernel sections, but we want to know the exact location of target objects. So unfortunately not now, but what we do as next step is we narrow down the granularity from 2 megabyte leakage to 4 kilobyte leakage. And before doing so, let's consider the memory layout in more detail. There are 3 sections. 3 sections are important for a lot of kernel exploitation. The first is the vmemmap. The second is vmalloc. Vmalloc is the memory region used for very large kernel object allocations. Vmalloc is mapped with 4 kilobyte mappings. Vmemmap is mapped with 2 megabyte mappings. And the third section is the DPM, the direct physical mapping. The direct physical mapping is a virtual mapping of typically the entire physical memory. It is used by the slab allocator. The slab allocator is mostly used for kernel heap allocations of smaller size.
So if we want to attack vmalloc, then we're basically already one step further, right? We already have 4 kilobyte pages.
Exactly. If our target object is allocated with vmalloc, then we can leak this 4 kilobyte offset of the object. One example is a bytecode for eBPF. And for other objects, we can use defenses.
What do you mean, use defenses?
Defenses can have side effects, unwanted artifacts, which changes the memory mappings of objects, let's say from 2 megabyte mappings to 4 kilobyte mappings. And we found that at least 3 defenses change the mappings of objects. And the first 2 are by design. So the first is the config vmap stack, which changes that the kernel stack is now allocated with vmalloc instead of kmalloc, which would have been allocated on a DPM. The second is the slab virtual. What it does, it virtualizes the entire kernel heap on a 4 kilobyte mapping. So these 2 are pretty straightforward. Just enable them, and target objects are now located on 4 kilobyte memory mappings. The third one is a more interesting one. It's the enforcement of the Linux kernel of strict memory permissions. Especially for kernel modules, a kernel module is not allowed to be writable and executable. That's one basic defense which we've learned a couple of years ago. And what this defense does is when the kernel loads a module to the DPM, so to the physical memory, it sets the permissions of the module code to not writable. However, if the DPM is mapped with 2 megabyte pages and the module code can be as small as 4 kilobyte, the kernel needs to split up this 2 megabyte section to 4 kilobyte mappings.
So is that what we're going to be attacking, the modules?
No, we don't attack the modules, but we use the modules to split a 2 megabyte page into 4 kilobyte pages where then our target objects are located.
Okay, so the module is just a convenient way to break up the pages with our objects of interest.
Yes. Yes.
So, but can we do that as an unprivileged user?
Yes, we can do it indirectly as an unprivileged user. We can access kernel functionality of modules which are not yet loaded by the kernel, and therefore load them now.
Okay, so let's go one step back. We can detect those accesses. How do we make the kernel access the areas of interest?
That's a good point. We use syscalls. So syscalls perform internal accesses of kernel objects and therefore loads the kernel pages of 4 kilobyte aligned kernel address into the TLB. There are some examples. When considering the kernel stack, we can just call an invalid syscall. This invalid syscall accesses the stack and therefore loads its 4 kilobyte aligned kernel address into the TLB. For the message object, we can use the message receive. The message object is a well-known object for kernel exploitation. Another well-known object for kernel exploitation is the byte buffer. For byte buffer, we just simply read from the file descriptor of this buffer, byte buffer. And for page tables, we can use mprotect.
And so we're usually interested in one page. Are these syscalls so convenient that they access exactly the one page we're interested in?
Unfortunately, no. All of these syscalls accesses a lot of kernel objects. Therefore, a lot of kernel pages will be loaded into the TLB.
All right, so there are a lot of pages. How do we find the one that we're interested in?
Let's consider one example, the example of the message object. As I said, the syscall message receive is a corresponding syscall which accesses the message. And what we do, we call the syscall with the identifier for message 0, and we want to leak the page of message 0. What the syscall does, it first accesses the IPC-NS, the interprocess communication namespace, and loads its address to the TLB. Then it accesses Q0 to load again its kernel page to the TLB. And lastly, it accesses our target object, the message 0, and also loads the target page into the TLB. As we see here, the syscall creates a distinct TLB pattern where 2 pages are unwanted artifacts, and 1, the page 2, is our target page. So therefore, what we do now, we perform another access. Now, to access the message 1 object, which is located on the same page, also on page 2, what the syscall does, it again accesses IPC-NS, it accesses Q1, and it accesses the MSG1, so creating another distinct TLB pattern.
So now we have 2 overlapping pages here.
Yes, we have the overlapping page 2 and 6. So therefore, what we do now, we call the syscall with an identifier object or with an object where we know it is not located on our target page. In our example, it's the message 32 with the Q32. And what we do now is...
Oh, so we just take the overlap between the first 2, and then we exclude the last one.
Yes. So let's show it in more detail. The set of pages accessed by the first syscall is 2, 5, and 6. Overlapping with 2, 4, and 6 is 2 and 6. And excluding 1, 3, and 6 results in our target page where both message 0 and message 1 is located.
So this seems pretty nice with 3 pages. Is this how many a syscall usually accesses?
Unfortunately not. So in our case, or in this case, the message receive accesses about 900 pages on multiple TLP levels. So a lot of more. What we have seen now, we are one step closer to our target of the location of the target kernel objects, where we can leak these 4 kilobyte aligned slab pages. In the former case, page 2 with the message 0 and message 1 object on it. And to get to the actual objects locations, what we do, we massage the Linux kernel allocator. We massage it that our target page, our target ideal page, only contains attacker-controlled objects. We do it by using a slab timing side channel.
So this is how we got that page full of green message objects before?
Yes.
Yes. So we don't know the order, do we?
No, we don't know the order, but we don't need to because we know the offsets where all of these objects are located. And as we show later, this is sufficient for reliable and stable kernel exploitation. And what we then did, we did a lot of evaluation of these location disclosure attacks. We evaluated on 3 Linux kernel versions, on v5.15, v6.5, and v6.8. We evaluated on a lot of Intel CPUs, while AMD CPUs and some ARM CPUs are also affected. We leaked the following kernel objects. We leaked the kernel stacks. We leaked multiple heap objects, like the message struct, credential file, seg file, and pipe buffer. All, also including the page tables or location of the page tables, all of these are interesting targets when considering kernel exploitation. And with that, we succeeded in solving the first challenge. So we start with where to write, and now we know exactly where to write. We want to write to these target kernel object as I shown before. So how do we solve the second challenge, Lucas?
All right, so let's look at this. So we're academics, of course, so we're not usually interested in doing the entire end-to-end exploit, and neither should you, because that's really bad. So we just give ourselves a leg up. We start with an exploit primitive ready-made for us, so we cheat a little bit. And so the one we're using here is the unlink primitive. So this is an unlink implementation for a linked list in the Linux kernel that is not always implemented in a secure way. So this will allow us to inject two values that the kernel then writes to some location for us. So this has been used to great effect with the bad binder attack and many others. And we're going to convert this into a read-write primitive. So in a little bit more detail, this is a linked list here of binder thread objects. And each of them has a list head with a previous and the next pointer. And so if we want to have the kernel remove the middle object here, what the kernel then does is replace the next and previous pointer of the first and third objects with each other so that the one in the middle gets cut out. So this is a normal operation here. But what if we, and this is the part where we cheat a little, can overwrite these two pointers in the middle? So we're going to overwrite them with dead beef and bad coffee. And then what the kernel will do for us is write bad coffee to the address dead beef and write dead beef to the address bad coffee. And so this is a very limited primitive where it does these two cross writes. And Lucas is going to tell us how we can make this into a nicer primitive.
Yes. Now, before explaining the exploitation technique to convert the unlinked primitive to an arbitrary read-write, let's consider the pipe buffer object. The pipe buffer object is the kernel object which stores metadata for every open pipe in user space. It stores a page reference of the physical back page where the actual data is stored. It also contains a read and a write end. These pipe buffers are located on slab pages of the kmalloc CG64 cache, which we leaked and messaged with our location disclosure attack. In our example, we see pipe buffer 0, 1, and 2 exactly in that order. We then use our unlinked primitive to overwrite the page reference. Instead of referencing the physical back page, it now references to the slab page where all this metadata of the pipe buffers are located. Then, if we write to pipe buffer 0, allows us to overwrite the metadata of pipe buffer 1. In particular, what is interesting, we can overwrite the page member, so the the reference or the page reference of pipe buffer 1. So what we do, we override it with our target page and then perform a legal read syscall and a legal write syscall to pipe buffer 1 in order to perform the actual arbitrary read and write. We can repeat this process, again writing to pipe buffer 0 in order to change our target page to something else. And that's basically how we create our arbitrary physical read-write primitive. And with that, we succeeded in solving the second challenge from what to write. We override it with a self-reference, in our case of the pipe buffer, in order to obtain the arbitrary read-write primitive.
All right, and now I'd like you to put your hands together in prayer to the demo gods, because we're going to do a live demo on the machine we're presenting on, because we're so very confident in the POC that we adapted to the latest kernel version yesterday evening. So nothing is going to go wrong. Lucas is going to put the exploit on the left-hand side, and the exploit is now going to ask for the bases, which he's going to do on the right side. So we're now leaking the vmem map, and it's already done. You can see this is pretty fast, and pasting this over here.
So
Now next, it needs the direct physical map. We're going to leak this. Also done. And finally, the code base. And so now this is the third part is where it gets tricky. We're using this message primitive again that we talked about before. And so we're doing this massaging now. Didn't work this time. Okay, it's running now. So this should spit out an address for a page where it has massaged all of these message objects.
oh,
It found an address. That's promising. So now let's hope it works as well. Okay.
And it worked.
An ID. Okay. Okay. Well, congrats. Okay. So finally, we've done our attack.
Oh, sorry.
And now we're going to look, to conclude this, we're going to look at mitigations. So we can mitigate this fairly simply in software by isolating the kernel and the user space from each other. And so for this, we can use functionality that's already in the Linux kernel, KPTI, kernel page table isolation, that was introduced for the Meltdown and Spectre attacks, but is today not really necessary anymore. And so what this does is basically just unmaps all the kernel mappings, the upper half of the virtual memory space, when we transition into user space, because the user doesn't really need those. So this transition, of course, has a certain overhead, and that's why it's not enabled anymore by default. A much more interesting solution is a hardware solution, like the new Intel LAS, linear address space separation, that simply looks at the most significant bit of the virtual address and knows that by convention, this is a kernel address, and so it can stop all of these accesses way before they get to the TLB translation stage, and thereby prevent TLB side channels. So to conclude, we've seen that defenses can have unintended side effects that decrease security. They hopefully also increase it somewhere else, but that's something to be mindful of. And similar for the allocator, the implementation can also help us amplify our attack. And finally, we've shown that we can put together side channel attacks with traditional kernel exploitation to remove some of the uncertainty and the guesswork there. So now we'd like to thank these nice people for giving us money, you for giving us your attention, and we have time for some questions, I think. So if you step up to the microphones, we'll take some questions. Thank you. Maybe our talk was very clear. Okay. Well, in that case, thanks again.
Thanks.
See you later.